Okay, I apologize for a second. I'll just try to arrange this. This is uncharacteristically talk with very little theory, and for good reason. We don't understand how to build a decent theory about it. So it will be mostly experimental observation and a little bit of hand waving. The most of the data are experimental, and they were obtained in the group of Michael Schatz in the Canberra and Australian National University. And we benefited very strongly from the discussion and critical remarks of Vladimir Lebedev and Derek Lindbergh. And this is on the theoretical side, and this is on the proper normalization of our data, on experimental data in Fourier space. Yeah, I'll probably use it. So it's what Peter told kink, and so it's one can argue whether there one see kink here, and this will be later. I will show you more of the data. This is experimental data that we get from our apparatus. I'll show you in a moment. Here is actually even two kinks if you collect kinks. The point is that by looking at a spectra, I cannot learn much, and it's a lot of discussions which are restricted on the level of looking into spectra are actually very could be very misleading, and it pays to have an experiment where you can really measure almost everything, and then you can look a little bit deeper on what is actually going on, and not just restrict yourself with a superficial similarity. So these two pictures shown aside, not because I expect them to be of a similar physical nature, maybe just opposite. I'm just saying that having similar spectra tells you practically nothing. So what is the experimental system that I'll be talking about? It's a two-layer, very shallow layer of electrolyte and even more shallow layer of dielectric. And this dielectric is just a lubricant. It serves to diminish bottom friction. And through this electrolyte will put current. And there are magnets. Here are magnets, and this is a view from above. We now, in the new version, we have 900 magnets. That's kind of a system which is the largest at this moment. This is 9 millimeters. This is the typical size of the magnet. So when we put current through, those magnets create force, and this would be a force scale. So the force scale is 9 millimeters in this system. And then we can work. The maximal size of our system is 30 centimeters, which is this 30 by 30 vortices. And typically, we would work with a box size. We can put walls inside, having box which is smaller or which is larger, because the most interest of this work would be what happens when you really have a mode, and it's a very strong mode, which is coherent across the whole box. The box size model. And for this, it pays to be able to vary the size of the box. So we have a removable walls inside that can make box in this interval. Okay, and we record everything, and it's a pretty sophisticated system of. There are actually two optical systems, and one optical system we control how many waves, so what is the variation of the surface, how two-dimensional is the motion, and another is which measured with high precision a two-dimensional velocity field. That's how it looks like. Just when you make a picture, this is how it starts. You see those vortices, which are magnet size. You wait for a while, you'll see some kind of a mess. You wait even longer, you see that on this mess something recognizable appears. This is in a pretty small box.
Are you continuing to force?
Yes, we force all the time. Let's say, for the sake of this talk, we force all this time. We can. And no, I just wouldn't have time to. So when you look at the total energy as a function of time, you see that it's apparently growing for some time. By the way, one can estimate here a rate of energy input of the system just by more or less estimating linear slope here. Then you see that energy saturates. At that time where it's still growing, when you look at the picture, it looks like this. At that time, it is over here. When it's more or less already saturated, you start seeing some kind of a coherent flow, which we like to call condensate because it's a spectral condensate. And then you can really vary the strength of this large scale condensate, which in this particular case is a vortex. We don't force intentionally vorticity, but the system is not perfect. There's always kind of a net rotation, so this vortex always has kind of a direction. Here, when we switch off everything, then we can look how energy decays, and this exponential decay gives us the rate of decay, which is actually bottom friction. And these three different data, they correspond to three different thicknesses of a lubricant layer, and just making it more thick, we can make this dissipation rate slower, and then we know that these are three dissipation rates. The energy was the same, but when you look here at this time, when we had a more or less steady state turbulence for these three different cases, we see that there are three completely different structures of this large scale monopole vortex. And of course, whereas the dissipation is the smallest, the linear friction is the smallest, we see the most coherent, I mean, really well-defined monopole vortex. But just to tell you that in this, something which you would not identify in any way as a vortex, when you average over, let's say, 30 turnover times, there will be 80% of energy which is left, which means that it's also very coherent flow inside. So it contains a large coherent component. Just your eye doesn't recognize it as such because it has a complicated special structure. So for a while, I'll start from this, which we call strong condensate, a strong vortex. We'll try to understand what is the structure of this vortex, how it actually lives, and how turbulence inside this vortex feels. And this vortex is completely creation of turbulence. It's fed by the inverse cascade, which because we put energy into the system initially only at small scales. Later,
you're not rotating, right?
No, we aren't rotating. Later, I'll show you we impose a large magnet and impose a large rotation, but not like this. But this would be because we try to model small scale input to large scale input. So far, only small scale input. 900 magnets switched on a very small scale. Now, when you average over 30 turnover time, a lot remains, surprisingly, and it's kind of clear, it's kind of coherent. And then when you look at omega as a function of r, this is mean vorticity, something which survives after averaging. You see that it's really has something which looks like a power law, and it's kind of on, well, one decade, let's say. It's not that good, but it's still decent. It's almost decade and a half. It's kind of fluctuating in space. Fluctuating maybe not the right word. It's a mean. It's something which survives after 30 turnover time. But it has this complicated structure, still looks like it's a power law. And now let me describe why we were looking for this power law. For this, I would mention works which this was in parallel with our first work, and then but before the second period article. This is numerics done by Conaton, who is now at Warwick, and these three Russian theoreticians. They did numerics in a purely two-dimensional system. In this case, they also have only small-scale forcing, but it perfectly forced the system with omega mean value equal to 0. As a result, what appeared as a product of inverse cascade was a dipole, because now a net vorticity is 0. And this dipole, now when you look into it, and then well, you try to resolve this structure of vorticity inside part of it, it also looks like this is 1.25, and it also has this type of a profile of vorticity. So it seems that there is something which is reproducible both in this numerics, which are purely two-dimensional, and in our shallow layer system. And here is a brief kind of a sketch of a theory, mostly done by Chertkov. Let's try to build a simple model which would tell us what kind of a structure we would expect. And so let's say that we take our total vorticity and subtract mean vorticity, omega, and take it squared. So it's a variance, what is around, and we call it h. Now I can write an equation for a mean vorticity and for this h, which is just a diffusion equation. I would say I'm now trying to describe what happens inside the vortex. Okay, there is some kind of a turbulence going on inside because of this age. Okay, and it somehow make a diffusion out of it. The point is that the diffusivity which stands here, d, it's of course it's a kind of spherical, I mean, axial geometry. It has r squared, and this lambda is something which is kind of a typically local Lyapunov exponent that would describe how systems separate. The point is that this local Lyapunov exponent, of course, depends itself on the level of turbulence, and it depends in a non-trivial way because it's a turbulence in a shear. I mean, locally, my large-scale profile omega, I expect omega to be a function of coordinates. It's a large-scale flow. This monopole vortex is this omega. So locally, when I look at the fluid element, how actually my vorticity blob is stretched, it knows that it is in a large-scale shear and in a small-scale turbulence. Now, the Lyapunov exponent, we can actually solve only two opposite limits. Kraichnan limit when we have a short correlated turbulence on top of a shear layer, or opposite limit when we have all very slow varying turbulence. In these two cases, lambda depends on h and omega in these two ways. Now we can plug this here and solve the resulting ordinary differential equation. And I think about it that it has a solution which is different for h and for omega, and it has a solution with h equal to constant, homogeneous turbulence inside vortex. And it gives vorticity profile which corresponds to a constant flux of vorticity inside vortex, constant in space. And it has a power law which depends on which actually regime. And of course, for turbulence, you expect this parameter to be of order unity. So one would expect this power law to be 1 plus 1/5, something in between of this. Which means that when we see and we really experimentally measure a power law decay, a profile of the vortex, which is 1 point something, like 1.2, and that kind of reasonably corresponds to this simple model. And the physical meaning of it is that actually vortex, it's a product of inverse cascade. But inverse cascade is something which happens in K space. Now it also tells you what happens in R space. In R space, it sucks energy in and it ejects vorticity out. That's what you expect of it to do, and that's what sustains this vortex. Of course, it would grow because it sucks energy in, but that this bottom friction stabilizes it. That's kind of a simple picture that one gets out of it. And now we start forcing. Now, if you look at K space of what I would just describe in R space, we have this something which looks like 5/3, and then kind of peaks appear here. If you compensate it here, it really looks like it's 5/3, even in this compensation. But sorry, in logarithmic scale, surely I need to do in this torture test. Then when we wait long enough, that's what we see as a spectra. And again, if I would remove these lines, whether Peter recognized king here or not, I guess it's kind of still recognizable without these lines which prompt the eye. And this is something which getting substantially steeper. This is a forcing scale. This is the forcing. Now we call it condensate, and for a good reason. If we take the mean flow average over many periods of large vortex, this completely disappears. So even though it's a power law which is something around 3, and we used to think when we look at power law spectrum, we say, aha, this is some turbulence, and we even want to say it's cascade. It's not. This part of a spectrum is completely determined by a coherent flow with a very non-trivial special profile. And that again, another type of a spectrum with a pretty strong condensate, as we say. When you average and take out the average, that's the spectrum which goes more or less continuously into this region. So all this bump was a condensate. And of course, this type of a flow already was observed in actually Bob Kraichnan probably the first who predicted that this phenomenon must exist, and Yachot and Smith, they observed it in numerics long ago at 90s. But this is kind of a simple idea that if you really take a mean value and you subtract it, then you see the spectrum. I'm not sure at all that this spectrum is well presented by 5/3. I put here kind of question mark. We don't have much of inertial interval here so that we can claim that it's 5/3. In numerics, they see kind of a less steep spectrum which is closer to -1. And theoretically, I would expect -1. Experimentally, we see something which is definitely not -1, but I would not bet that it's -5/3. And it's really very frustrating that I cannot derive it. At least I cannot derive anything which looks like experiment. So now I want to just show a few simple estimates and go beyond spectra to describe higher moments. But let's start from the second moment. And so if I would like to understand where this kink, where this knee would be, I would say that I need to compare the contribution into second moment of velocity difference of my large scale flow, which means that at a distance r, it would just scale as r squared because it's a kind of a smooth large scale flow, with this small scale turbulence, which for no other reason, I still kind of use Kolmogorov scaling, but let's say there is something here which is less than unity and larger than 1/2. Then just comparing this, I would estimate a scale where I would see a crossover from large scale contribution to small scale contribution. That would depend in this way. Now, I would estimate this large scale flow. This is a typical mean gradient of a large scale flow. I would estimate it just from energetic consideration. I would say that as much at least, this is actually inequality. I say that I have a cascade which carries energy backwards, and this is somehow must be dissipated. It's not an equality, not even an estimate, because it assumes that the whole energy flux is local, and it's not guaranteed now that I have a large scale vortex. It can really, this large scale vortex can directly suck energy from small eddies, not waiting when it brings it by cascade. Okay, but at least it would kind of give an estimate, and then I would say that if this gives me alpha is a bottom friction coefficient, so that would give me V, and that would give me S as V over L, and then when I plug it here, it gives me what would be a wave number where I expect this knee in the spectrum. Yeah?
You have measured all these quantities.
Ah?
You have measured all these quantities on the right-hand side. Yeah. You have measured L, you have measured C, you have measured alpha, you have measured epsilon.
What do you mean?
You have measured your
Measured.
experiment.
Yes, yes. Yeah.
So if you plug in the numbers.
Yeah, that's what I show. Yeah, that's precisely the next slide. Yeah, absolutely. So now here I know L, it's the size of my box. I know coefficient alpha, as I've shown, as I told you, I measured it from here. I just know in seconds. I know what it is in inverse seconds. Okay, and then I can really look at the spectrum. Not that it's kind of that clearly defined when actually trying to evaluate this and this. One can put it here or put it here, so it's up to something. But qualitatively, it corresponds to this, up to a factor like to this formula. It corresponds, let's say, up to a factor 1.5, let's say, of order unity factor. And of course, it shows the right dependence. So as we go from alpha, which is smaller, from alpha which is larger to alpha which is smaller, we see how it changes over here. When we change the size of our box, again we see how it changes. But this was about spectrum. Now if we try to guess how the existence of this large scale flow would influence the other moments, and particularly the third moment is of interest because it would give us a measure of energy, of a local part of an energy flux in our system. And then we can kind of, it's not even an argument, it's a kind of hand-waving dimensional type reasoning that we will say that if I have a small scale contribution, just would be turbulence and nothing else, then the third moment would just behave as epsilon r, where epsilon is a energy dissipation rate. But then if I would really consider third moment without subtracting the large scale flow, it would have this type of a cross correlation because it's it's not isotropic and uniform system. There is a correlation between turbulence and large-scale flow inside, and we estimate it as SR for delta V, and as this again Kolmogorov type estimate for, because I don't know beta, and that would give me L star, which I call the scale at which I would expect my third moment to be spoiled by condensate. Which means at smaller scales I would expect turbulence to dominate. At larger scale I would expect my large scale vortex to dominate the third moment of velocity difference of a third structure function. Now what is important is if I look at the ratio between the scale where I spoil my third moment and the scale where I spoil my second moment, this is of course dimensionless number, and it's an inverse Kolmogorov constant, which is, or another way, it's kind of mean skewness. And mean skewness is known to be small, or Kolmogorov constant is known to be large. So just for this reason, we expect that the spectra would be spoiled at much larger scale, and the third moment would be spoiled much, much closer to forcing because of this. And this is indeed what we see. So that's our third moment. This is the total third moment. We can look at longitudinal. It looks more or less the same. So when we look here, we see that it's in our turbulence region where this is our forcing somewhere here. Here we expect this moment to be positive, but it's negative. It has kind of a wrong sign here, and it's kind of getting near zero at smaller scales. And this is the third moment obtained in the unfiltered flow, which means the flow which contains vortex inside. Now we can take this mean value, we can get the mean flow, we can subtract the mean flow, and after that we can look at the third moment. And then we see that indeed all the way up to forcing scale it's positive, which corresponds to inverse energy cascade. We know that we have inverse energy cascade with force only at small scales, which means that there is no question for us where we put energy into a system. We want our data to demonstrate it. And indeed, when we really do this filtering, we see that it really gives us a positive, well, a decently linear moment, and it's getting, of course, negative when we go below the forcing scale. And then again, here, this condensate estimate, where we expect the condensate to dominate, it's here, and we see that it really changes its dependence. It's not linear anymore. It's not that. So, and in a sense, that I'll now return to this famous picture of Lindbergh and Cho, that where they've seen this. It's logarithmic, so that's why it's kind of, they inverted it, but it's a kind of a negative part. So I don't think our system have very much in common, but definitely, qualitatively, it looks like this negative part. This negative part is something which is obtained from unfiltered data. If I would look at it, I would say that I have a direct cascade here, because my third moment is negative. Now, when I filtered when I took out this coherent large-scale flow, which is very strong, I do see an inverse cascade, which I know is a true answer. And this particular lesson, I believe that it's very difficult to do this with observational data from atmosphere or ocean. But I believe that without kind of filtering out mean flow, anything that you say about high moments, particularly flux, would be just meaningless because of this strong contribution of cross-correlation between. Now, it's interesting also to look at how much I'm doing. 5, good. Of course, interesting to look at higher moments, and this is in particularly flatness, and this is just kind of what we would see if we would kind of what we call weak condensate, which means not such a huge vortex, just kind of some kind of correlated flow. And then we may see how it looks when we increase the strength of the vortex just by decreasing the bottom friction, and that's how flatness would behave in an unfiltered signal, and it looks like it's nicely, it's practically Gaussian here, and then this is a turbulence domain. Now, when we subtract, we see, of course, we have something very coherent and fluctuation on top of it. If you don't subtract this coherent part, it looks like it's not strongly fluctuating system, because you have a huge coherent part in it. So if you really want to know how fluctuating the system is, which is flatness is a good measure, then you do subtract, and then you see that it's actually much higher. And in this respect, we may now compare this flatness of a turbulence without this large-scale vortex and with this large-scale vortex. It's not a very good comparison. Again, I'm not sure, and nobody really knows what is the nature of this turbulence. It seems like it's close to 5/3. I don't have any good theoretical reasons why it should be close to 5/3 inside this very non-trivial power law profile of vortex. But using this as an estimate, the flatness actually increases when you are inside vortex, which physically I believe is reasonable, because what this large-scale flow does, it distorts vortices. But it distorts strong vortices much less, because if you have a strong vorticity inside, you don't really, you cannot stretch your vortex and kill it. And as a result, you kill weak vortices, and strong vortices survive, and that leads to the increase of flatness. So in a sense, in this respect, I believe that at least qualitatively, on this level, we understand. And now just last minute, we want, not that we really want to model atmosphere, it's not atmosphere, but we also wanted to have an input on a large scale. So what we did here, we put a big magnet, a system size magnet, on top of our system. So now we can have an input on a large scale and input on the small scale. And then what we see, first of all, that when we put this external flow, the level of turbulence jump, it suppresses it very strongly. Just this, not vortex which appeared because of inverse cascade, but vortex that we imposed on it, this large scale vortex, it really suppresses turbulence. It's quite clear why it is. But then when we again do all this subtraction, etc., we see that still the third moment has a positive slope. So even though we have now large scale force and small scale force, when we look at energy flux inside, energy still flows backwards in R space. And again, the flux suppressed, but it's also suppressed because we have magnets, and this large magnet, it sweeps vortices with respect to the forcing magnet. That's why it's actually suppressed the flux. And here's kind of a summary, and it's not very satisfactory in the sense that we cannot really say much about it, just kind of a general mumblings that condensate suppress turbulence and then can enhance and suppress fluctuations. There are systems in which condensate, like in superconductivity type systems, the condensate actually suppresses fluctuation. Here we see that the condensate enhances fluctuation because this strong shear kills weak vortices and keeps strong vortices, and it actually enhances the relative level of fluctuation. And that's more or less what we measure and what we understand. Not much, I guess. Thank you.
Okay, time for a couple of questions. Right.
Yeah, it surprises me that you got the transition wave number right, because I took the figures you have in your paper and plugged it in, and I got a value which was about 100 times smaller than the predicted.
Transition wave number?
Yeah, the transition wave number. I just took the values from your paper, plugged them in to the formula with my pocket calculator, and I got a value which was 100 times smaller than the observed.
Again,
I can show
must
you.
be because of normalization factor. But I really advise in all this that it's probably that some data in Fourier space are pi squared different. But then you use data from R space, which means that what you really need here. I mean, look, what you need for this formula is, let me show you to you. What you really need, you need epsilon, and epsilon is very easy to get. Just you see how energy grows. You can get it from the. You don't need spectra for this. You took data from spectra, and that's why that's probably
I took the epsilon from
pi
the
squared.
structure function.
And yeah, but that's what I'm saying. That if you just take this epsilon, now this alpha, you again, it's inverse second. It's actually
But
one.
you get it. You have it in
Yeah,
your paper.
and you get it. And this is the size of the box.
Yeah, which is well defined.
Yeah,
I think
And
you
you-
need to
you-
take this, talk about this privately.
that's pretty straightforward.
So, Michael.
I didn't quite catch your forcing units time dependence, but in any case, there may be some resemblance between your system and the kind of model that Brian Farrell and Petros Ioannou have been plugging all their lives. They say it models everything, but I think it might model your system because you have some kind of forcing and a great shear that keeps shearing the forced small-scale vortices, and of course that gives you your upgradient momentum transport of the energy, the vortex sucking in the energy. Might be worth.
Well, yes, I mean, that's more or less the picture, but look, we have inverse cascade before any large vortex appears. I mean, just we have inverse cascade in this system just when we have enough bottom friction to absorb, and then we don't have any vortex. So
Okay,
it's not a problem in a shallow layer. And by the way, any three-dimensionality at least 4 orders of magnitude less. But when vortex appear, then it influences this inverse cascade.
Yeah, so that's the mature stage.
Yeah,
I guess
yeah.
that's what I'm talking
Yeah.
about.
Yeah, when we are talking about the suppression of turbulence by the large-scale flow, we are to distinguish the effect on the forcing and the effect on the turbulence itself, because in the experimental system, the input of energy is not given.
Absolutely.
Yes, you reduce also the input of energy because you reduce the correlation between vortices.
You're absolutely right, and that was in the first period that we just measure, and for this we impose this large vortex. There we can clearly see that just by sweeping vortices with respect to magnets, we decrease an input of energy. Yeah, exactly, and we can measure it.
But the other question is, with a given input of energy, do you reduce the turbulence? If consider a given input of energy unchanged?
The answer to this, yes, but not with a high accuracy, unfortunately. So if we take the data which corresponds to the same energy input rate, which we estimate, then one may ask how the turbulence level at a little bit larger scale look, and it looks like it's a bit suppressed. But unfortunately, this is an answer which is got with not much accuracy, and this is something which we are working on.
Okay, we have a more general question from Eric, and then
Yeah, my more general question. My general question is the role of viscosity here, because I think it's a very viscous flow. The effective Reynolds number is very low. If you estimate the viscous dissipation in the so-called inertial range in the k to the -5 range, it's of the same order of magnitude or even larger than the energy flux through the
I'm surprised that you raise it again, because I already answered twice. So let me answer it again. The energy dissipation due to viscosity is something which is nu k squared. So if you put here a forcing scale, then this nu k square is comparable with a typical turnover time of vortices on this scale. It's in our experiment, and it's Stabile experiment. You cannot get a large Reynolds number if you want to have a big inverse cascade. Now, if you take wave number which is 3 times less, you can get something which is 9 times less.
You calculate the dissipation.
That you do it in an incorrect way.
No,
Well, Eric,
I just integrate.
let's take it
Look, I mean,
offline. Let's